Dear students, today we will be studying the use of aliphatic nitro compounds in synthesis. Since we are discussing the disconnection approach, that is retrosynthesis, where we are thinking both ways, forwards as well as backwards in both the direction. So at times things are seeming a little problematic or complex, and we are trying to come out of this complexity. So we must remember the words of Winston Churchill before starting, who had said long time back that problems are just opportunities in disguise, and the optimist, they seek opportunity in every danger, whereas the pessimist, he sees a danger in every opportunity. So we are the optimist. We should be optimistic that yes, we'll find a solution as one goes along, trying to make things easy, changing the complex compounds into the simple starting materials. First of all, we'll start with this. I'm showing you this. You'll wonder as to why I'm showing you a carbonyl when we are studying nitro compounds. Well, because we know that carbonyl enolizes fast and easily, and because of that it has great synthetic importance, because we can easily form carbon-carbon bonds after enolization. But the thing is, why it creates a problem, because the carbon is positive, so it acts as an electrophile. There are many syntheses where we do not want such a thing to occur. So how can that be managed? Well, by means of this, the aliphatic nitro compounds. As we can see in the aliphatic nitro compounds, and the common ones are of course this only, nitromethane and 2-nitropropane. The rest can be synthesized from these. Here nitrogen is positive, so this will make the alpha carbon acidic. In the presence of this will form a carbene ion, like this alpha carbon does in the case of carbonyls. But here the similarity ends. Why? Because in this case, this carbene ion which is formed is being stabilized by, we can say, two groups. That is, the stabilization of this carbene ion is twice that which is present in the case of a carbonyl carbon. So it is a very stable carbene ion, because this nitrogen cannot be attacked by any other, it can't act as any other group. So this is very good stabilization. Hence, this can be used for a number of very good syntheses as well. Let's see now this nitroalkane. We know on reduction it gives us the NO2 group. We've used it earlier in our functional group interconversions, and the NH2 to the NH2. So this is a hidden functionality. That is NO2. When we write NH2, actually many a times we are implying NH2. So this functional group is hidden behind this, so it is known as a latent or a hidden functionality. Secondly, this was the discovery of McMurray in the year 1973, that when aliphatic, these nitro compounds, they are catalyzed by titanium chloride. In that case, they lead to the formation of these ketones. Ketones, this is in other words, CHCO now. So this is an CCO. This is acyl anion equivalent, like the acyl functionality. So this was here NO2. In place of NO2, now we have got this carbonyl. So this was an important discovery. Earlier on, these used to be prepared by Neff's method. Now, we know this is acidic, this alpha hydrogen. So in the presence of a base, this will give us the carbene ion. So a method of stepping up, like in the case of acetylenes, similarly here, so that this is now carbon negative. In the presence of a base, this is R positive. So this will lead to the higher functionality, the higher nitroalkane. And this, when reduced, will give us this RCH2NH2. So taking these aspects of, or these special characteristics of our aliphatic nitro compounds, we will be trying a few problems of retrosynthesis where this will be applicable, that is the use of aliphatic nitro compounds. Now this is one molecule which is chlorphentermine, this target molecule. This is used as a diet suppressant. We can see at one end of the benzene ring there is Cl, at the para position there is this CH2, C, NH2, CH3, CH3. Now as soon as we see this NH2, we are reminded of the latent functionality of NO2. So we convert it by FGI to NO2 because we know that by reduction we can get this. Then what can one do? A 1,1-cc disconnection so as to simplify this further. This disconnection will lead to this carbon positive here and carbon negative here. Why negative? Because we know this is attached to a nitro group, so we will easily get a carbon negative over here because the alpha hydrogen here is acidic. So this will lead to carbon positive and carbon negative. These are the synthons and these are their respective synthetic equivalents. This is then the disconnection. Now let's do the synthesis. The synthesis starting with this nitroalkane in the presence of a base. This will lead to CH. Over here CH, H will be removed. So we will get C negative. C negative will therefore combine with this benzyl chloride. Here this will be C positive. So we will get this product. This on reduction will give us the target molecule. Now let's move on to the other retrosynthesis. Now this here 1, 2, 3, 4, 5, 6 and it is bridged. And this is phencomphamine. This is actually, this was by the Merck company, started off as a special use for depressive fatigue, that is tiredness due to depression, the daytime depression for that, because it has very less side effects, though now it is not so much in use. Because many other, since that time, a number of other compounds which are better as far as results are concerned, they have been manufactured or synthesized. So see, in this case, there is this NHET at one end, 1,2 position of this ring. And this is the phenyl group. So what will we do? First of all, we will disconnect, because disconnection at the heteroatom is done at the first level. So we will disconnect this from this, Rx disconnection. So the Rx disconnection, and we will disconnect it because we know now that this can be connected back very easily by use of a carbonyl. A carbonyl with this will give us this type of a group after reduction. It will initially be the amino NH2 and CH3CHO. So H2O will be given away. So we write the Rx between the N and the CH2, CH3, this carbon CH2. Rx disconnection, this will lead to NH2 because N will be positive being a heteroatom. N will be negative being a heteroatom. So H positive will stabilize it. So this will be NH2. Now the other part, that is the CH3CH2, so here CH3, rather than the CH2 we write then CH3CHO, because we know that H2O on returns, we are thinking the back reaction, and this H2O this will give us this imine, which on reduction will give us this amine. So after this, how can this be then further disconnected? Now this NH2, we know NO2 will give us NH2. So again NFGI and NO2. Now once, and this is a cyclohexane ring, whenever there is a cyclohexane ring, such rings, then, and see there are these two, which can be disconnected at two ends. So it can be disconnected here, it can be disconnected here. So we will get this as the ene and this as the diene. So that proposes a Diels-Alder reaction. Now 1, 2, because these two carbons are now disconnected. So we get 1, 2, 3, 4 and this bridgehead carbon. So in other words, this is now we get a cyclopentadiene, the bridgehead carbon forming this point. So cyclopentadiene plus this will be the ene. So this is diene and this is the ene. Hence the Diels-Alder reaction. This is connected to, and this is of course, this will be transene, NO2, the stable one, at one end, and the other bulky pH group at the other end, having trans geometry. Can we disconnect this further? Now as soon as we see these two again, NO2 as we did earlier, and this other group, automatically we connect it at alpha beta level. Alpha beta, these two carbons are disconnected. So we will get C6H5, CH, and in place of double bond O. So we will get double bond O. And the other end, of course, here will be 1C. So the compound, nitro compound for that is nitromethane. So CH3, because that CH3 being then can in the reverse, we have to think of the reverse, can then form what? H2 by H2O. This will be given off, so this double bond can be formed. Now let's start with the synthesis. The synthesis is what we disconnected last, will be the first step. So this is C6H5CHO plus CH3NO2 in the presence of a base. Here we will get H2O, so a double bond with C6H5 at one end attached to this CH here, then the double bond, and the other end is the NO2. This of course, this is the ene, which cyclopentadiene will give us the Diels-Alder reaction. These two ends will therefore, this will be connected at this end, this at this end. Cyclization therefore giving rise to this compound, because the double bond is now changed to this single bond ene. Rather than the diene, it is now an ene. And at this end we have got, where there was a double bond, an NO2 and a phenyl ring. These two. And now this on reduction will give us NH2. This NH2 on condensation, this NH2 with CS3CHO, which we earlier removed. So this will give us first CH, see this is CH, so over here with this NH2, and this on reduction, this will be reduced, and we will get, rather than the imine, we will get this NH, CH2, CH3, our target molecule. So this was the synthesis of this target molecule which we undertook, this target molecule which is used for depressive fatigue by means of these disconnections, which were finally simplified to these two starting reagents C6H5CHO and CH3NO2, which together reacted to give us this trans product in the presence of a base, which on dialder reaction gave us this dialder product, having the same because it is stereospecific, so the trans geometry was retained. Now this on reduction gave us this reduced NO2, the latent functionality NH2, which with CH3CHO and finally reduction led to the target molecule. Now let's see the use of nitro compounds in Michael addition. Michael addition. Now Michael addition, here we have got this CO, again this is a 1, 2, 3, 4, 5 membered ring with NH at this end. So let's disconnect it, RX disconnection. This is carbon over here, this is X, the heteroatom, which will lead to CO, this is CO stabilized to this COOET, the ester, because this will be carbon positive. So here we attached C2H5, this is the ester, and this N negative H will be stabilized with H positive, so this is the synthetic equivalent. Now NH2, again NH2 functional group interconversion to NO2. On going back we'll do reduction, so we'll write that. Now let's see, count the number of carbon atoms. This is carbon number 1, 2, 3, 4, and this NO2, so this is acting as an in place of like a carbonyl, you know, so we can count it as the fifth one. So this will be disconnected in a 1,5 dicarbonyl fashion, in that manner, 1,5 dicarbonyl manner, and alpha beta next to this will be disconnected, because this will give rise to again this nitro compound. This nitro compound here, and at this end a double bond. Why a double bond? Because see, we are producing what? We are producing here, this end will produce a carbene ion negative, and this giving us an alpha beta unsaturated, because this is C double bond O, OET. So C double bond O, this is the alpha position, this is the beta position. So this will lead to an alpha beta unsaturated carbonyl compound and this other compound. So this compound here, which we have written, will be the Michael acceptor, accepting the carbene ions from this nitro alkane. Let us see now the synthesis. This is the Michael acceptor. So this is CO. It was CO when we disconnected. So this was changed to the synthetic equivalent OET. OET is the negative because this carbon was positive. And the double bond here to facilitate the reaction, because it was disconnected from this end. So this was negative, this was positive. This hydrogen ion left taking this positive charge. So this developed therefore leading to the development of this double bond. So this leads to an alpha beta unsaturated carbonyl compound, which is the Michael acceptor. Since there will be electromeric shift in this direction, so this double bond will come here, and this terminal, this carbon will get a positive charge, where the carbon negative from the nitroalkane can attach, therefore giving rise to this type of a product. So this is Michael addition, and this was the Michael acceptor, this alpha beta unsaturated. Now this on reduction will give us the NH2, and this NH2, H from here, C2H5O negative from here. So cyclization will lead to the formation of this target molecule. So this was the use of nitro compounds in Michael addition. The use of nitro compounds in Michael addition, and this is the synthesis starting from alpha beta unsaturated carbonyl compound in the presence of a base to give this Michael addition product, which on reduction will give us this NH2 COET, the H from the nitrogen, the ethoxy from the carbon will lead to cyclization. C2H5OH will leave, and therefore we will get this cyclic product. Moreover, there are not only this, there are other uses also where, as we discussed earlier, there is the use of TiCl3 titanium. So let's study one example where we are using titanium chloride for this type of a retrosynthesis. This is the compound. Now this compound, cyclic compound, again cyclohexane, a double bond. When we see this, immediately Diels-Alder reaction comes into play, because at this end now there is this carbonyl. We know that this carbonyl can be converted by if NO2 is attached here, NO2 can be converted to carbonyl by TiCl3. So we will write this in the forward direction, thinking about what we will be doing in the backward direction when we are synthesizing. So FGI, rather than writing CO, one writes NO2, because NO2, as we did earlier, studied that NO2 in the presence of TiCl3 will give rise to this carbonyl. Because this becomes so positive, it leaves, so in the presence of titanium chloride. So this functionality it gives rise to. Now this can be disconnected at these two ends. So Diels-Alder product, that is a double bond here, a double bond here, and a bond here. So these two will be formed, the diene and the dienophile, with NO2 at one end and CH3 at the other. This on alpha beta disconnection will give rise to, this is CH3, CH and double bond O. When there is a double bond O, immediately this other carbon will be CH3, one carbon nitrate, so CH3NO2. These two together will be therefore are simple starting reagents. From these two we can synthesize this ultimate R product, the cyclohexene derivative. Let's start the synthesis. CH3CHO with CH3NO2 in the presence of a base will give rise to, because here this is NO2, H2 from here, O from here, so this trans product. This dienophile will add to this diene to give us the cyclic derivative with NO2 at one end and CH3 at the other. This, on reacting with NO2, what we did earlier in the functional group interconversion, is converted into the carbonyl derivative. So we get the target molecule. This was about the retrosynthesis using TiCl3 in this case, because earlier we didn't do any of these examples. So I hope we recollect the use of aliphatic nitro compounds by way of its latent functionality, that is conversion of NO2 to NH2, and formation of the acyl anion equivalent, that is TiCl3, because in the presence of TiCl3 we know that NO2 can be converted into CO. That was the point we used, that was the property we used over here for this disconnection that we did.